Hello and welcome to this lecture series on microprocessor and microcontroller. So we are currently studying 8086 microprocessor and we are in the 19th video lecture of the complete series. So this is ninth video lecture on 8086 microprocessor. So up till now we have completed a lot of things. We have completed the programming portion of 8086. We have completed the architecture. We have completed the pin diagram. We have completed maximum and minimum mode operation of 8086. We have completed the interrupt structure, etc. So now it is the time to do the last thing, which is let us completely study the instruction set of 8086. So 8086 has a very rich instruction set if you compare it with 8085 microprocessor, and that's what we are going to study in the coming few lectures. Maybe three or two of them will be dedicated for studying the instruction set. And together with instruction set, we are also going to study addressing modes in 8086 today. So let's begin today's lecture by just having a look at, first of all, what do we mean by addressing modes of 8086. So as we have already clearly studied in 8085 also, that addressing modes, what we mean is, suppose there is an instruction, an assembly language instruction. So in that instruction, you might be willing to read or write some data, right? You might be willing to read or write some data. So from where would we obtain the address of that data? So that's what we mean by addressing modes. So we are only interested in finding the address of the data that we want to use. So depending upon how do we obtain that address, we classify instruction based on these addressing modes, right? We classify instructions based on that fact, that how do we find out the address of the data that we want to operate on. So depending upon that, we have these 7 different addressing modes in 8086: register addressing, immediate addressing, direct addressing, register indirect addressing, direct register relative addressing, base index addressing, and relative base addressing mode, relative base index addressing mode. So since we have done a lot of programming exercises by now in lectures as well as labs, so these might not seem very strange to you. So let me just begin by register addressing. So an example of register addressing is move bx comma cx. So in this move bx comma cx instruction, we already know that the format is move destination comma source. So bx happens to be the destination here and cx happens to be the source here. So the data from cx register will be moved to this bx register. So we are trying to operate on the data which is kept in cx, and we are trying to copy the data into bx register. So that is why the address of data is, if it would have been externally interfaced memory, there would have been an address. But we all know that if the registers of the microprocessor are used, the registers which are inside the microprocessor, then they don't have an address, right? So that is why this mode of addressing is called as register addressing mode. I mean, the data which we want to operate on is kept in some register, and that register happens to be CX register, and you want to transfer it to BX register. So these two registers are used. That is why it is called as register addressing mode, right? So now let us see immediate addressing mode. So we are again using the same command of move bx comma 1234h. So at first glance it appears that these two move instructions are doing the same work. Essentially they are trying to put some data into bx register. But the important point to note in this second addressing mode is that here the data that we want to move into the bx register, it is 1234h, and it is present there in the instruction itself. You don't have to look for this data into some register, or it is not kept in the externally interfaced memory. So it is given in this instruction only. Although, yeah, so this is given in this instruction only. The data is given in this instruction. That is why this mode of addressing is called as immediate addressing mode. So you don't have to look anywhere to find out the address of 1234. It is there in the instruction itself. Then the third mode, again by using the same command, move cx comma 1234 and inside brackets. So we know that what will this instruction do, since we have done some programming exercises by now. So we are aware that if 1234 is kept in big brackets, then what will happen is it will access a location inside the data segment whose offset will be 1234H, right? So from that location, it will copy the 1 byte, sorry, from that location and the next location, it will copy a 2 byte data into CX register, right? Had it been only a 8-bit register or 1 byte register, the transfer of data would have taken from only 1234H to that register. But now, since this is a 16-bit register or a 2 byte register, so in this particular case, data from location 1234 and 1235 in the externally interfaced memory will be copied to this CX register. So that's what this command will do. But here we are talking about what addressing mode it will be using. So the addressing mode used would be direct addressing, right? Why is it direct addressing? Because the address from where we want to obtain our data is directly given in the instruction, right? So there is a difference between this previous version and this version. In immediate addressing, the data itself was available. Here 1234 is treated as data, and here 1234 is being treated as address, right? So this is there. So this 1234, you can also put a H after that because it should be in hexadecimal. So you can put a H after that. So that is mandatory here. So now after that, what do we need to do is register indirect addressing. In this register indirect addressing, you see here it is similar to the previous command, but move cx comma in brackets si. So si contain an address, and that address is being used here for taking maybe 2 byte or 1 byte data depending upon whether you are using 1 byte or 2 byte register here. So from those two locations which are pointed to by SI, that data from those two locations will be copied into this CX register. So that is why it is called as register indirect addressing, right? So register because a register has been associated, SI register has been associated here. So similarly, we have got direct or register relative addressing, right? So you read the name register relative. Register will be there as well as the addressing will be relative. So you see this instruction move SI and then 0002H comma 92H. So we all know that this instruction will simply move a data of 92 in hexadecimal to the externally interfaced memory, and the effective address of that particular location inside the data segment will be given by summation of SI and 0002, because if you know, if nothing, no segment is specified before this, the default segment will be data segment where this offset address has to be used. And there you can see there are two brackets, so the data of SI and 0002 will be summed up, and whatever is the effective address, so at that particular offset inside the data segment, your 92H will be moved. So effective address is something which you calculate after adding these two. So that effective address will be added to the base address, that is the beginning of the data segment, and on that physical location, this 92H will be transferred. So here you can see a register is involved and an offset of 2 bytes is involved. That is why it is called as register relative addressing. So register is there as well as some relative offset is given. So this offset is not mandatorily of 2 bytes. It can also be of 1 byte, right? So it is up to you what you want to use. You can use a 1 byte offset or you can use a 2 byte offset, right? So that's why we call it as register relative addressing, or an alternative name is direct relative addressing, right? So the next thing is base index addressing. In base index addressing, one of the base registers will be used, that is BX or BP registers will be used, and index means one of the index registers will be used, that is SI or DI will be used. So you have got this command move BX bracket SI comma 93H. So the effective address will be calculated by summing up BX and SI, and the data segment the data segment's base address will be there, and to that base address this effective address, that is contents of bx plus si, it will be added to calculate the actual physical address, and to that particular physical location in the externally interfaced memory 93H will be moved. So this is called as base index addressing. Next is a higher version of it, relative base indexed addressing. It is actually a combination of this 5 and 6. that is register relative addressing and base index addressing. So if you combine both of that, you will get relative base index addressing. So here you are using one base register, and then you are using index register, which is SI. So index is there. Then you are using a relative term. So relative term, it could be of 1 byte or 2 byte. So that way you have got this relative base index addressing in 8086. So these are all the addressing modes of 8086, and they will be applicable to different instructions. So let us now see what is the instruction set of 8086. So as I already told you that this instruction set will be very rich as compared to 8085. So let's first have a look at in how many parts this instruction set has been classified. So there are about 100 instructions in 8086. So they can be classified into these major 8 classes. These major 8 classes are there. First is data copy or transfer instructions. Move instruction is a part of this particular group. So these instructions are just used to transfer data from here to there inside the microprocessor. So we'll see a list of that, and we will study some important point about each and every instruction in this particular group. So the second classification is arithmetic and logical instructions. So this arithmetic logic instruction set is also very powerful as compared to 8085, because as we saw in 8085, we only had this addition and subtraction instructions, but no multiplication was there and no division was there. So we have to separately make a program for that. And in fact, it did not take care of the fact that whether you are multiplying signed numbers or unsigned numbers. So in this, everything of that kind will be taken care of. So then the next instructions are branch instructions. Branch instructions means instructions like jump. So if you want to jump to some particular memory location, if you are inside the data segment and you want to jump within the segment, so you can jump to another location inside data segment. Or if you are inside data segment and you want to make an inter segment jump, so you can jump into maybe extra segment. So that is also possible. So on that way, we have got near and far jump. Like in the function calls, we have discussed that we have got near call and far call. So similarly, in these jump instructions also, we have got near jump and far jump instructions, right? Then, as we have already seen in our programming exercises, that there are dedicated instructions which are dedicated for looping. So those looping instructions are there, which we will also see. Then there are some machine control instructions. One such example of machine control instruction is halt, HLT. So HLT will halt your computer. So that's an example of machine control instructions, and HLT is not the only one. There are many more instructions we will see in this category. So after that, we have got flag manipulation instructions. So in this, when we discussed the structure of flag in the very first lecture, I guess, we have discussed that O, D, and T, these flags can be controlled by the user. So there are some commands which are dedicated for dealing with the flag register of 8086 microprocessor. So we will see, right? So one such example could be CMC, which means complement the carry flag. CMCs complement the carry flag. So one such example of flag manipulation instruction from 8086 instruction set is CMC. Then we have got shift and rotate instructions. So these instructions are similar to the instructions that we have studied for 8085, where inside a register, we try to shift the binary bits of that particular register either to the left or to the right, with or without using the carry flag inside the rotation. So these shift and rotate instructions are there. And then after that, there is a dedicated class of instructions which is called as string instructions. In these string instructions, we will be seeing the instructions of how to store the string inside memory, how to display it on the screen, etc. So on and so forth, right? So these string instructions are very important. And if you see this data transfer or copy instructions, string instructions are also a part of this. And if you see these any of these set of instructions, some string instructions are associated with every set. So instead of taking the string instructions with every set, we have dedicated a class for that, which is called as a string instruction. So This is broadly speaking how we classify 8086 instruction set. Some people consider this arithmetic and logical instructions to be in separate group. So they may call it that there are nine different classes of instructions in 8086. So it's just a matter of how you number them and order them, right? So now in today's lecture, our whole sole aim is to first of all study this data copy and transfer instructions and arithmetic instructions. The logical instructions and the rest of the things will be discussed in the coming lectures. So we won't be studying every instruction in great details, but we will be touching every instruction. We will be illustrating its purpose, and if there are some important points associated with that particular instruction, we will be definitely uh, exploring that. So let us first begin with this data transfer instructions, right? So these instructions that you see here, 14 instructions are there for data transfer, or copy instructions are there. So we are going to study them one by one. We will touch every instruction. And I have marked this star here because there are some string instructions also which will do this data transfer, but we will study them in a separate section which is dedicated to string. So let us begin by our very familiar and very frequently used instruction move. Move destination, comma, source. So this is the format for the data transfer and copy instructions. Whenever you specify two operands here, one of them have to be destination, another has to be source, right? So destination, comma, source, this ordering will remain. So whenever move instruction is executed, the data of source will be copied to the destination. It's not cut and pasted. It is copied to the destination from source to destination. So the flow of data is in the backward direction. So some important points about this move instruction are that destination and source both cannot be memory locations, right? Although it is possible that destination is one register and source is one memory location. So you are transferring data from memory location to the source, or sorry, memory location to the register, or the vice versa. But both of the locations cannot be memory, because if externally interfaced memory is there and you want to transfer the data from one location of externally interfaced memory to the another location of externally interfaced memory, then you cannot bypass the microprocessor. Data has to come inside the microprocessor in its internal registers, and from there it can be copied, right? So these source and destination, they cannot be both memory sources, memory locations simultaneously, right? Second important point to note about it is that move ds comma 1234h, this is not allowed. If you use any segment register which is related to either data segment, code segment, extra segment, or stack segment, you cannot move immediate data into those four segment registers directly. You first have to use a general purpose register, and you have to move 1234 into that general purpose register, and that general purpose register can be copied into them by using move dx comma ax. Suppose you have already moved 1234h into ax register by using one move command, and then you can copy move ds comma ax. So segment registers cannot be initialized directly. One might ask, why is this so? Why we can't just move immediate data into these segment registers? It would be very easy. Why are we using these two steps? So the point is, the designers of this 8086 microprocessor, they were a little careful about mishandling of the segments that you create in the externally interfaced memory, right? If they give you the capability to change the value of this ds or cs or extra segment or stack segment by moving immediate data into it, then there are chances that inside your program you might probably transfer the immediate data into these registers, and that would practically imply that you have just moved the beginning of data segment from one location to another location. So this should not happen frequently, because if this would have been allowed, it wouldn't have been an error. It wouldn't have been an error, and you won't be able to debug your program easily. So they were a little careful about mishandling of these externally interfaced memory segments. So they didn't allow this thing to happen. So whenever you want to transfer the data into this segment, you can't use this directly. And even if you do, it will flash an error, so that you will become careful that this is a segment register, and by changing it, you agree that you want to change the beginning of that. So that is the reason they haven't allowed this instruction. Then the next instruction is a push instruction. So push, you already know it is used for stack operations, and in 8086 as well as in 8085, we know that whenever we want to push something onto the stack, it has to be in 16-bit format, right? So it will be using the two consecutive locations of the memory. So push source can be register or memory, and it operates on word. So we already know that whenever we put 2 bytes onto the stack, uh, it is actually last in first out list. So in that, if you put 2 bytes onto the stack, the stack pointer will be decremented by 2. We have already seen this. And the data will be kept onto the stack in little endian format. By little endian format, we mean that higher order byte will be kept at higher order address, and the lower order byte will be kept at lower order address, right? Similarly, the pop instruction is there. It performs the reverse operation of push instruction, and similar reasoning is there for this pop instruction also. So we have already discussed these instructions. That is why I'm a little bit fast in covering these. Whenever I will encounter a new instruction, I will elaborate on that. Now, apart from this push and pop, which pushes and takes data from the stack and to the stack, we have got push F and pop F instruction also. What will this push F instruction do? Push F instruction will simply push the flag register onto the stack. If at any point you want to move to a subroutine or you want to move to a procedure, then in that case, it is a good practice to put the contents of flag register onto stack and then move there, right? So this push F instruction will do that. And whenever you return from that particular subroutine, this pop F instruction will pop 2 bytes from the stack into the flag register in the little endian format. So this could be useful when you make function calls, but not all of the times you would require to push your flag onto the stack when you move on to a certain procedure. So if it is useful for you, you may use them. So push F and pop F without any space or gap between push and F and pop and F is used. So these two additional commands are there. They were not present in 8085. Then this XCHG instruction is for exchanging. This was also there in 8085, and the format is destination comma source. So whatever is destination's content, it will be kept into the source content, and whatever is source content, it will be kept into the destination content. Now, destination and source both cannot be memory locations. Both can't be memory locations, and immediate data is of course not allowed, right? Because if you use immediate data, then immediate data is a part of instruction, so you can't change the instruction while the program is running. So these 2 points should be noted with this XGHG instruction, that destination and source both cannot be memory locations because we cannot bypass the microprocessor. Memory cannot itself transfer data from one location to another location, so microprocessor has to be involved. Microprocessor has to be involved means its internal registers have to be involved. So that is why these two cannot be your both memory locations, destination and source. And immediate data is of course not allowed, because if you want to, if suppose the source is an immediate data, then source will be copied to destination, but where will destination put the data? Because immediate data does not have uh, anything like address, right? So you can't store it into the place of immediate data. So that's not possible here. Then again, this is a very interesting command: load effective address, and then you can put any register here: AX, BX, CX, DX, etc. So what is this load effective address? So just now we have seen various addressing modes. So let me also move again to that slide. And you can see that you can just use memory locations in various format. One such format is bracket SI, then 0002H. So the address of SI plus 0002H will be added, and then the effective address will be calculated. So in the data segment, you will be moving to that particular offset. Similarly, you have seen that this is also possible. You can have a 1 byte offset, then you can have BX and SI register, or you can have BP and SI register, or you can have BX and maybe DI register. So any combination can be used. So these three have to be added, and effective address will be calculated that way. So in the instruction set, in data transfer instructions, you have got load effective address inside the register of BX and DI. So suppose you are using this combination BX and DI. and whatever is the effective address after their addition, it will be loaded into the register that you will specify here. The register, of course, has to be a 16-bit register, because ultimately this BX register and DI register will be able to keep a data of 2 byte or 16 bits individually. So effective address will be calculated out of these two, and it will be kept in this register. So you can readily use it somewhere. So it comes handy in a lot of situations. So load effective address is there. Now the next two instructions that we are going to study, LDS and LES, are a little bit confusing if you do not remember them properly. So pay good attention to these two instructions. Now LDS. LDS is LDS B. First of all, let us see this instruction: LDS BX comma 3125 inside brackets. So what is going to happen here is LDS contains DS. Now, so DS register and this BX register that you have written here, they will be loaded with some data. Now, BX register is of 2 bytes and DS register is also of 2 bytes. So we will be needing a total 4 byte data, right? We will be needing a total 4 byte data. And from where are we going to obtain that data? So you see here the address 3125 that is written here. So in the data segment at the offset 3125, and so we take four memory locations. This is 3215, 3216, 3217, and 3218. So this is not 3125, this is 3215. So let me keep it 3215, 3215. So this is 3215. So we have taken four memory locations: 3215, 16, 17, and 18. And inside these memory locations, 1 byte data will be stored, right? So that 1 byte data will be copied to BX register and DS register. So first BX register will be filled and then DS register will be filled. And BX register will be filled in little endian format, and DS register will also be filled in little endian format. So BX register means the lower byte of that will have the data which is kept at 3215. Higher byte will have the data which is kept at 3216. And similarly, after that DS register will be filled, so it will have data at 3217, the lower byte of that, and higher order byte will have higher order data. So this is what this LDS BX will do. So it will first load BX and then it will load DS register with the four consecutive memory locations that have been given by this in the data segment. Similarly, if you look at this next command, lesbx, 3125, right? So here it will also again use the same format. So let me also make it this 3215. Yeah. So this will also again be working in the same format, but everything will happen inside the extra segment because it has got load extra segment and BX. So BX will be loaded first, then extra segment will be loaded, and both of them will be loaded in little endian format. So for this command, it happens in data segment, and for the next command, the drama happens in extra segment. So these two commands are useful somewhere in some special kind of programming scenario where essentially you are trying to get the base as well as the offset address of some particular segment, or you might have kept them onto the data segment or extra segment for your usage. So these two statements are rarely used, but yeah, they are there. So after that, we have got this LAHF instruction. Now this LAHF instruction, it has got this AH register. So you can see it as load AH with flag. Now this is an inconsistent statement. Why is it an inconsistent statement? Because AH register is of only 1 byte or 8 bits, because it is the higher order AX register. So AH register is the higher order AX register, so it is only of 1 byte, and you want to load that AH register with flag. Now flag here is of 16 bits or 2 bytes. So a 2 byte data cannot be loaded into a 1 byte register. So what it essentially means is the lower byte of the flag register is loaded into AH, not the higher byte, right? So the lower byte of the flag that we have seen in 8086 is exactly similar to the flag register of 8085. In 8085, we had an 8-bit format for flag register: carry, parity, auxiliary carry, then 0, and then sign, right? So the same format is there for this register in the lower byte of the flag register, because in 8086 we have a 16-bit flag register. The lower byte is similar to 8085, and we have got this overflow, direction, interrupt, and trap flag in the rest of the higher order byte. So we are not talking about the higher order byte here. The lower order byte of the flag register will be copied to the AH register after the execution of this particular command. And the reverse of that will of course happen by SAHF, store the contents of AH into the flag register. That means lower byte of the flag register. So this AH, whatever content it will have, that content will be copied to the flag register. So this is also a kind of a flag manipulation command. And if you see the instruction set, you have got these flag manipulation instructions. So but then this is not covered there. It could be although put there also, but we are classifying it as just a data transfer or copy instruction, right? So because if you set or reset some flags in the flag register by using this command, obviously the operation of microprocessor will be affected. So that can also be put into that category, but conventionally it is kept here only. Now this instruction, the next instruction, 12th instruction, which is called as xlat, is interesting statement. So it is actually used to implement some lookup tables, right? So let me just demonstrate this particular instruction to you through an example. So this is a program to understand xlat instruction, and what xlat instruction does is it will create some lookup tables. So what do I mean by lookup tables? So lookup tables are something like this. For example, uh, when I say 1, I should mean 10. When I say 2, I should mean 25. When I say 3, I should mean 1000. So you have a table, right? You have a table which has a key value pair. One is key and another is value. For 1, I want to mean 10. So 1 is the key and the meaning is 10, right? So that is the value. So key value pair is there. So if somebody says 2, then you should mean say 2000. So 2 is the key and 2000 is the value of that. So if you have a key value pair and you have many such key value pairs, then you have got a lookup table. For every key you have a value. So to be able to implement that lookup table kind of thing in 8086 microprocessor, you have got this xlat instruction. So let us first see how xlat instruction performs. So for that, your data segment needs to be initialized, which is of course the case because the data is kept in data segment register by default. So data segment is initialized. Now in BX register, you should keep the offset address from where you want to start your lookup table in the externally interfaced memory, right? And in AL register, you should keep the offset after the offset which is kept in BX where you want to access that, right? I mean 5000 is kept in this DS register. So the actual physical address from where data segment starts is 50,000 because a 0 by default will be appended because of the address logic that we have discussed. And at 50,003 location, your lookup table will begin. And you want to access the 50,008th location. That means 5 location after the beginning of lookup table. So that is why you have kept 5 here. So this 3 plus 5 will be 8, right? So that way this lookup table works. So let me just emulate this code and demonstrate it by an example. So your data segment has begun from 5000 and the offset is 0000. So your lookup table as per this code, should start from 0003H, because if you keep some data into the BX register, then this is the requirement of this xlat instruction, that BX and AL registers should be appropriately initialized, right? So I'm going to location number 5000 and 0000 in the data segment. That means because I have initialized it that way, so I am starting from this 50,003 location, I am putting some random values. Let me put a value of say 1 here. Then at the next location, let me keep the value as 2 there. Then at the next location 3, and then at the further next location, let me keep the value as 4. Then at the next location 5, then 6, then 7, then 8, and so on and so forth. I can just go up to complete filling of 256 bytes. Sorry, 256 bytes. Yeah, because this AL register can have that many number of combinations in itself, so that can be done. Now see what this code will do. So let me just run one step, and you can see here that at 50,003 one is there, and we are interested in 50,008 location. So 6 is stored there, right? So remember this, at location number 50,008, 6 is stored, and we are talking about the base address as 50,000h. Then after the offset from where the table starts is 0003, and we are interested in location number 05. That means 0003 plus 05 is 0008. So we are interested in this particular location. So the data kept there is 6. So let's execute this. So up to now, the data segment has been initialized. So you can see it that your data segment register has been initialized by 5,000, and let me execute these two commands. So BX and AL register have been appropriately initialized. You can see that BX contains 0003 and AL also contains 05. So this is A lower, which contains 05. Now the moment I execute xlat instruction, whatever content is kept at this location 50,000 plus 3 plus 5, that is 50,000 at H, it will automatically come into the AL register. So this is the default register for this xlat command. So let me execute it, and you can see that a 6 has appeared here, right? So similarly, now if I want to access, say, the sixth location in the lookup table or the seventh location in the lookup table, I just have to initialize AL appropriately, and I can do that. So lookup tables are useful in some programs, and you will find them useful in some of your programs. So this instruction is there, xlat instruction, and it's not that you cannot make lookup table without using xlat instruction. You can do it, I mean, in ample number of ways, but this instruction is there in case you have a very simple lookup table of the kind we have just discussed. So it creates lookup tables, and it uses bx as the start of lookup table in the data segment and al as the offset after the bx register, right? So this is the meaning of this xlat instruction. After that, you have got in and out instructions. So these are special instructions which I will further elaborate in some laboratory session through some interfacing examples. But as of now, if we talk about 8085 microprocessor, the data bus there was of 8 bits. So that is why we had 2 raised to the power of 8. That is a total of 256 external devices can be combined with that microprocessor, or can be interfaced to that microprocessor, right? However, in 8086, since you have got a data bus which has got a size of 16, so 2 raised to the power of 16, that is whatever is that number, right? So 2 raised to the power of 16 externally interfaced devices can be connected to this. So to be able to deal with them, we have got this in and out command, and to those devices we assign some port numbers, right? We assign some port numbers. So these port numbers can be of 1 byte, or I mean, 2 bytes also. So you can take or give data to them through these registers. So this is in and out command. I will further elaborate on them in some laboratory session. So as of now, you can just take this information that because of 16-bit size of the data bus, the external interface devices can be 2 raised to the power of 16 in number, and they are named by their port numbers, and through their port numbers they can be accessed, and data can be transferred to or from them through in and out commands. And you're already aware of how in and out command can be used in 8085. So in more or less same way, we will be able to use this in and out command for 8086 also, right? Now string instructions we will be discussing in separate section, although there are some instructions in string instruction set also which can copy and transfer data, which are a part of this data copy transfer instruction set, but I intend to discuss them in a separate session where we will be only talking about strings, nothing else, right? So this completes discussion on data copy and transfer instructions, and most of these instructions are easy and we have used them, and some of the instructions like xlat and LHF and maybe this LEA, LDS, LES are new, which we haven't used as of now, but I have just elaborated them, right? So now let us come to this arithmetic instruction set. Now arithmetic instruction set is also very rich. We are going to discuss 17 important instructions out of that, which is a complete arithmetic set of this 8086. And there are good concepts that we will learn with this. So you can see here I have drawn some tables here which will be enhancing our understanding of arithmetic instructions. Let me begin by these simple instructions: add al comma ah. I don't need to elaborate on this, I think, because we have used this several amount of times. Uh, you can put either 1 byte registers or 2 byte registers on both the sides, or one memory location and another register, and so on and so forth in this add instruction. The format remains the same: destination comma source. So whatever is the result, it will be stored in destination, that is in the first register, and it will be performing, of course, the addition of two numbers. Similar to this instruction, we have got an instruction called as ADC. This will also perform the operation of addition, but it will also involve the carry flag, right? So it will add these two numbers BX and CX, the numbers which are kept in BX and CX, but it will also add with these two numbers carry flag, right? So this will be helpful for us in the cases when we design a program for addition of 32-bit numbers or 64-bit numbers, because the carry which will be generated out of one word, it could be added to the next pair of words by using this ADC command. So in those calculations, this instruction might help us, and otherwise also this instruction is useful. So these are simple instructions. I am not elaborating anything on that. After that, we have this increment instruction. So increment will simply increment the value of the register by one, right? The only point to note here is that we can use a memory location or a register of either 8 bits or 16 bits. So that can be done here. And if a register of 16 bits has got a value of FFFF, and if you try to further increment it, it will become all zeros. So that should also be kept in mind, right? So again, these are circular in nature. Now, similar to this ADD, ADC, and INC, we have commands for subtraction, subtraction with borrow, and decrement, right? So I don't think that I need to elaborate much on them because they follow the exact similar format as we have seen in ADD, ADC, and INC. The only thing is they are involved in subtraction. So SUB will subtract the two registers that you have got, and the subtraction will be destination minus source, not source minus destination. So the first argument will be, I mean, the second argument will be subtracted from the first argument. That is, destination minus source will happen. Similar case for SBB, but it will consider the borrow flag. That is the same as carry flag, but in case of subtraction, we call it as borrow flag. So it will take the borrow flag into consideration, and DEC will decrement whatever is written after that. It could be a 1 byte or a 2 byte register or an external memory location, and so on and so forth, right? Now, this is an important command: NEGAL. NEG means negative, and AL or AX or whatever is written after that. So it will negate, I mean, it will form the negative of whatever is written inside this. So how will we find out the negative? So there are various ways of representing negative numbers in binary logic. So the way that we will be following is we will just take out the two's complement of the number, right? So that's what we mean by this NEG instruction, negate. So we will form the 2's complement of this number, and we already know what 2's complement is. In the binary representation of any number, if you flip every bit, that is, if you change 0 to 1 and 1 to 0, then that number becomes 1's complement of that number. And if to the 1's complement you add 1, then it will become 2's complement for a binary number. So for a binary number, the process of obtaining 2's complement from the binary representation of the number is this: you flip every bit, and to the result you add 1. You will be able to get the 2's complement. And that's what this negate command will do. This negate command will form out the 2's complement of whatever is placed inside the argument. So this is a fairly simple command. And after that, we have got CMP, destination comma source. So compare destination comma source. We have already discussed compare command for 8085, and from there, if you recall, compare command, it performs exactly in the same way as it worked in 8085. So what will happen is compare command is nothing, but it is subtraction command only, where destination minus source will happen, but the result will not be stored in destination. This is the only difference. All the flag registers will be set as they are intended to be set, and from those flag registers we can just take the result of comparison without disturbing the content of this destination flag. So destination minus source will happen. If destination is equal to source, the result will be 0, but it won't be stored in destination. Only the 0 flag will be set. If destination is greater than source, then in that case, carry flag will not be set, because carry flag, if destination is greater than source, then there will be no borrow which will be taken to accomplish subtraction. So carry flag will not be set. And if destination is less than source, of course, your carry flag will be set, in which case it is called as borrow flag. So that way you can just get the result of comparison through various conditional statements or conditional branch instructions that we will soon see, or maybe in the coming lecture, right? Then, now this is an important command: multiplication and signed multiplication. IMUL means signed multiplication. So multiplication, you can see that there is only one argument. This is not possible because we have to multiply two things. So the thing here is that we have a default register here, in which uh, one of the registers will be the source registers that you will keep here. Another register will be a default register. So that default register in case of 8086 happens to be AX register, right? So if you are accomplishing a one byte multiplication, that means your source register is of 1 byte, then in that case you do not have to use complete AX register, you have to use only AL register, right? And after multiplication of AL and this 1 byte source register, the result might be of 16 bits. You are multiplying to 8-bit registers, but the result might become of 16 bits. So that is why the result will be stored in AX register. So remember this: when you are trying to multiply two 1 byte numbers, one of them is kept in this 1 byte source register, and other is kept in your AL register. After the multiplication, the result will be stored in AX register, right? Similarly, if you are trying to multiply uh, two numbers which are of 16 bits each, so in that case, one of the data will be kept in AX register, another data will be kept in this 16-bit source register, and after multiplication, the result might go up to 32 bits. So the result will be kept in a combination of DX and AX register. The lower order of the result will be kept in AX register, and the higher order of the result will be kept in DX register. So DX AX combined is the default register for multiplication when you are trying to multiply to 16-bit numbers, right? So this point should be remembered. Now, after that, you have got this IMUL command, which means you have to take signed numbers into consideration. So this is essentially multiplication, but signed numbers will be considered here. Similarly, you have got this division command, which exactly work on the same default as multiplication. So whenever you're trying to divide a number which is of, say, you have kept the number in this uh, AL register and you are trying to divide it by a source of, say, which is again BL register. So after the division, the remainder will be stored in AH, that is the higher order byte of AX register, and the quotient will be stored in AL register, right? However, if you are trying to do the 16-bit calculation, then in that case the remainder will be stored in DX register and the quotient will be stored in AX register, right? So this works similar to the multiplication command, and it has also got a counterpart which will take signed numbers into consideration. So I division is also there, right? So these are fairly simple instructions. Now comes the instructions which we need to elaborate further. So before discussing these last instructions from 13 to 17, let me just give you a glimpse of some basic fundamentals that you must be already aware of. If you talk in decimal systems, then the basic numbers, they begin from 0, 1, 2, 3, 4 and continue till 9. So after that, if you are short of numbers, you have to start making combination. After 9, 10 comes. That means you combine 1 and 0, then 1 and 1, 1 and 2, 1 and 3. So that way you make combinations. So the basic digits, the digits of decimal system starts from 0 and end at 9. Similarly, if you talk about hexadecimal system, the digits, they start from 0 and they actually go till this 9, and after that 9 they do not have 10. We have got A, B, C, D, E, F. That means 6 additional numbers are introduced here, which are alphabets, right? So this is the hexadecimal system. Now Another representation of numbers is binary coded decimals. So it is ultimately a decimal number. I mean, the numbers will start from 0 to 9, but they all will be in binary coded form, 4-bit binary coded form. So 0000 till 1001. So this is the binary coded decimal, right? In hexadecimal number system, you can also find out 4-bit equivalents like this. So up till 9, they will remain the same. But a will be 1010, B will be 1011, and so on and so forth. F will be 11111, right? So, but now this number's binary equivalent will not be valid BCD number, because BCD number is just a decimal number. After 9, there is nothing called as A. If you want to make a number, say 12, then then 12 will be represented in BCD as 0001. After that, you have to put 0010. So that 8-bit number will be called as 12 in binary coded decimal. So digits cannot go beyond 9. So this is a general fact about this binary representation of numbers, which I guess you must be already aware of, right? The second thing we want to be aware of is BCD number, which can be written in two formats: packed BCD and unpacked BCD. Let's first talk about packed BCD. For example, the numbers that we have just talked about, they are similar to packed BCD. So if you want to represent 39, 39 is a decimal number and you want to represent it in a packed BCD format. So what you have to do is you simply have to represent 3 in BCD format, which is 0011, and a 9 in BCD format, which is 1001. So this is the representation of a packed BCD number. And why is it called as packed? Because if you see 8085 computer or 8086 computer, the externally interfaced memory, it has got every location which is 1 byte, right? And here you are essentially putting information of 2 digits into one number, that is 3 and 9. So that is why we say that we have packed two numbers into this 1 byte. So this is called as packed BCD. However, if you talk about unpacked BCD numbers, then instead of taking the 4-bit equivalent of 3 and 9, we will take 8-bit equivalent of 3 and 8-bit equivalent of 9. So it will consume 2 bytes, but it will be a wastage of these 4 bits, because the initial 4 bits will never be used, because 9 is 1001 and it can be accommodated in the last 4 bits only. After 9, there is nothing in BCD system. So these 4 bits are wasted. But in computers which have got a 1 byte capability, you some of them use this 8-bit representation for BCD numbers, which is called as unpacked BCD numbers. So you have actually a BCD number, but it is unpacked. I mean, it is consuming more byte than it is intended to consume, right? So this is what we mean by packed and unpacked BCD numbers, right? Now, after this, let's come to this particular command, decimal adjust the accumulator, right? So some explanation has been written here. You can look on this yellow chart, and here I'm explaining this DAA command. Suppose inside the microprocessor, you want to add these two numbers, 39 and 12, right? Obviously, we know that whatever we write inside microprocessor is visualized in hexadecimal, and at base it is in binary numbers, right? So whatever we write here, 39 and 12, if you want to add them through this command, in AL you have kept 39 in hexadecimal, in CL you have kept 12 in hexadecimal, and through this add command you are adding AL and CL and keeping the result in AL. So after addition, the result will be obviously 4B, and that will be in hexadecimal. Now, what if I want this addition to become in BCD numbers, right? If you have added 9 and 2 in hexadecimal, it became B. But if you will add 9 and 2 in binary coded decimal number, or actually in decimal number, 9 plus 2 will be 11, and the result will be 1, and 1 will be carried here, right? So this would be 3 plus 1, which will be 5. So 51 should be my answer if I want the calculation to happen in decimal, or actually BCD. So here you see the representation. This is 39 in hexadecimal, this is 3, and this is 9, and similarly 12, this is 1, this is 2, and this is actually, if you see the BCD representation, this has to be like this. The BCD representation has to be like this, right? And on addition in hexadecimal, you will get this number. Coincidentally, the BCD representation is as good as hexadecimal representation for this particular case. But if you treat them as BCD numbers. I mean, if you treat 39 as BCD number and 12 as BCD number, then 4B is not the actual result. The result has to be 5-1, right? But actually, when microprocessor will add these two numbers, it will treat them as hexadecimal and it will give you this particular result, which is 4B. But if I want to obtain the result in BCD system, unpacked BCD system, then what will happen is I have to apply this command DAA. What will DAA do? It will see if the valid numbers in this BCD system are up to 9. So if any number is greater than 9, we can see that there are 6 digits after that. I mean 6 more numbers after that. So it will shift that number by 6 so that it will become a valid hexadecimal, valid BCD digit, because anyway it will come here then, right? So what will happen here is if the result that you have obtained after hexadecimal addition, if it is not a valid BCD digit, as you can see here, 1011 is greater than 9. 1011 is not 9. So it will add 6 to it, that is 0100. And here you can see that 0100 is fairly within the limits. It is less than or equal to 9. So here nothing is to be added. So DAA will do this. If the number that you see in any of the nibble is greater than 9, then it will add a 6 to it, right? So this is one condition. The second condition is either the auxiliary flag or the carry flag. If it is greater than 1, then also 6 will be added, because if auxiliary flag or carry flag is greater than if auxiliary flag or carry flag is 1, that means there has been some carry or auxiliary carry. So in that case also this 6 has to be added. You now understand why 6 is added, because you see that after 6 digits, if you cross these 6 digits, then you will again reach to this location, so it will become a valid number. So that 6 is added there, and then you can see the result is perfectly okay. This is 5 and this is 1, so 51 it is obtained in BCD. So you are putting the numbers inside microprocessor in hexadecimal 39 and 12. The result, if you want to obtain in BCD system, then you have to use this DAA command, so it will automatically readjust your result in this format. Similarly, if you see this command, this DA is complete. This DAS is for decimal adjust after subtraction. So it is similar to DAA, but it works on subtraction instead of addition. After that, similarly, we have a command which is called as AAA, ASCII adjust after addition. So like in this case, we have done a decimal adjust after addition. We can also do ASCII adjust after addition. And you all might be aware that this numbers from this 0 to 1, sorry, 0 to 9 in ASCII system, 0 will be 30, 1 will be 31, 2 will be 32, 3 will be 33, and so on and so forth. 9 will be 39, right? So if you want this 34 and 38, they are written in hexadecimal format, but if you treat them as ASCII number, this is actually ASCII 4 and ASCII 8, right? So you want to add them and obtain the result in ASCII only, right? So however, whenever they are placed inside microprocessor, they will be added in they will be added in hexadecimal system, and you will get 6C. But you are not expecting a 6C here, because if you add 4 and 8, you should get 12. So 4 and 8, if you treat this 34 as ASCII number and 38 as ASCII number, so this is 4, this is 8. 4 and 8, when they are added, you will get 12, right? So on hexadecimal addition, 6C is obtained. So if you use this command AAA, the result will automatically come out to be 12. 1 will be in the carry flag, and the 0010, that means 2 will be stored in whatever register you have added it, right? So how is that done? Let us see that. So this AL and CL, 34 and 38, its equivalent is shown here. So this is ASCII 4 or hexadecimal 34H. Similarly, this is ASCII 8 or hexadecimal 38H. When they are added, you have got 6CH. So this is the representation of 6. This is the representation of C. But this is in hexadecimal. We want the result in ASCII. So again, ASCII will use the same logic that we have used in this DA command, with one additional thing. It will it will not see this 3, that is it will mask this 3, so that this will become 4 and this will become 8. So that masking procedure is implemented, and it does not see the higher nibble of the data, and it will simply add these two numbers. And if the addition is greater than 9, it will set the carry flag, right? So here you can see that if you add these two numbers, the result is 1100. So definitely the auxiliary carry will be set, but auxiliary carry will be copied to carry flag in this case. and that after setting the carry flag, since the result that you have obtained was greater than 9, so you will add 0 1 0 0, that is 6, which comes from this previous logic. So it will perfectly become 0 0 1 0, which happens to be 2. So in carry flag you have 1 and you have 2 in the register, that is AL register after addition. So this is how this AAA instruction, that is ASCII, adjust after addition. You are entering the numbers in hexadecimal, but you want to be treated them like they are ASCII numbers. So ASCII numbers, if they are added, you should also obtain the result of ASCII number. So for that purpose, this ASCII adjust after addition is used.